let's also see the derivation of LMTD for counterflow heat exchanger. So we will use a similar derivation. Only difference is that in the end one, hot fluid enters and the cold fluid exit. So end one is the cold fluid, hot fluid entry end and cold fluid exit end, whereas end two, cold fluid, hot fluid exit and cold fluid entry. So end one is always chosen as the end where hot fluid enters, and the end two is the end where hot fluid exits. So it's always with reference to the hot fluid entry and the exit, we choose the end one of the heat exchanger and end two of the heat exchanger for parallel as well as counterflow. Now follow a similar procedure. Yeah, we have yeah. By following dq for a counterflow heat exchanger, delta q can be written as minus m dot c into c. I took this together in as a single term, and the subscript is written common for both these. So delta q is equal to, sorry, yeah, m dot h into ch into dth, m dot h into ch into dth, which is equal to minus ch dth, or dth is written as minus delta q divided by ch. Here again we can see that the hot fluid, when it flows from first end to the second end in the positive direction, this is negative. This is delta, this slope is negative, so in order to make this positive, we introduce a negative sign, so that delta q is equal to minus ch dth as before, or dth is written like this. Whereas in the case of the cold fluid in counterflow heat exchanger, cold fluid enters at the second end. So when you see from the first end to the second end, our positive direction, the cold fluid temperature also decreases from the first end to the second end. So this direction, the positive direction, is to be taken care of for cold fluid. So for cold fluid, dTc will be negative, because this is our positive direction, and the in counterflow cold fluid flows in the negative direction. So delta q is equal to minus m dot c cc into dtc, which is equal to minus of cc dtc, or dtc is equal to negative delta q divided by cc. Here, while deriving this, here you should take care to incorporate this negative sign for the cold fluid, because its flow direction is opposite to the in the negative direction. So that's why we needed to use a negative sign here also. So now equation 1 and equation 2 as before. Uh, yeah, subtracting dth minus dtc, dt is equal to d of th minus tc, is equal to minus of dq into 1 by ch plus 1 by cc, 1 by sorry, minus of dq into 1 by ch minus 1 by cc. 1 by ch minus 1 by cc. Let's call this, so in this derivation I have written this as first equation. Now delta q as before can also be written as u into th minus tc into dA, where th and tc are variables. th varies from thi to tho, and tc varies from tho at the first end to tco at the first end to tci at the second end. So that you should keep in mind always to incorporate the sign in the proper way. Otherwise, we may not get the correct answer while deriving it. Now, this dq is written as u into th minus tc dA, and combining equation 1 and 2 and rearranging, we will get d of th minus tc divided by th minus tc is equal to minus of u into dA into dA, u into dA into 1 by ch minus, sorry, this is wrong. This should be cc. There are some mistakes like that. Okay, this is 1 by ch minus 1 by cc. 1 by ch, 1 by cc, h, c, etc. Okay. So d of th minus tc divided by th minus tc equal to minus of ua 1 by ch minus 1 by cc dA. Now we need to integrate this. So on integration, integrating from end 1 to end 2. On integrating, this will be logarithm of th minus tc within the limits is equal to minus u into 1 by ch minus 1 by cc into integral of this is area, total area of the heat exchanger. Now how do we apply the limits? So log of final minus initial. Final is the end 2. End 2 is the end where the hot fluid exits. Now you have done two steps in a single equation. Integration, there was a negative sign here. So there was a negative sign. I took this negative sign to the left side of this equation. So this will turn out to be logarithm of THO minus TCO. THO minus, so it should have been like logarithm of THO minus TCI by THI minus TCO. It should have been like this. But this negative sign which was there on the right side is taken to this side, so that logarithm of THO minus THI minus TCO divided by THO minus TCI. I hope that the students has no confusion over this, because when we students has no confusion over this, because this negative sign, when we take the logarithm, it will become the reciprocal. Logarithm of reciprocal will be negative of logarithm of the original thing. So there is a slight, there may be a slight confusion, but you just write this over here and make sure that this is the equation. Logarithm of THI minus TCO divided by logarithm of THO minus TCI is equal to UA THI minus THO minus TCO minus TCI divided by Q, and this has to be rearranged. We'll go to the next slide. Q is equal to, see, Q is taken to the left side. Q is equal to UA into this term divided by the log term here. Q is equal to, only Q is retained in the left side of the Q equal sign. So UA, the numerator, divided by this log will be taken to the right side. So that will become Q is equal to UA into, see, THI minus THO minus TCO minus TCI. THI minus THO minus TCO minus TCI divided by log of this thing. THI minus TCO, THO minus TCI. Now, this should be rearranged. THI minus TCO. We will write like this. THI minus TCO minus THO minus TCI. THO minus TCI. THO minus TCI divided by log of the same thing. See, why we write like this? Why can't it be like this itself? Why do we write like this? So here we can see that U into area into what is THI minus TCO. THI is the temperature of hot fluid at the first end, inlet end, and TCO will be the temperature of the cold fluid at the first end, because the cold fluid enters at the second end and leaves at the first end. So if you take the temperature difference of hot and cold at the first end, will be THI minus TCO for a counterflow. And also temperature difference between hot and cold fluid at the second end. So second end minus THO minus TCI. So that's why we rearranged the numerator of temperature differences like this. So divided by the same thing will be coming for the log term also in the denominator. So UA THI minus TCO divided by THO minus TCI. So now this stands for the mean of the temperature difference between hot and cold. Mean of the temperature difference between hot and cold for the counterflow heat exchanger. So for counterflow heat exchanger, Q can be written as UA delta T. Mean of the counterflow. What type of a mean is that? This type of a mean is called the log mean temperature difference. So delta T mean of counterflow is equal to THI minus TCO minus TCO minus TCI divided by log of THI minus TCO minus THO minus TCI. This is called a log mean temperature difference for counterflow heat exchanger. Log mean, CF stands for counterflow heat exchanger, delta T. So it's like this. So now we can consolidate the results for parallel flow and counterflow. In parallel flow heat exchanger, delta TLM, log mean temperature difference LMTD, is THI minus TCI minus THO minus TCO divided by log of THI minus TCI by THO minus TCO, natural log. Whereas for counterflow, THI minus TCO minus THO minus TCI divided by logarithm of THI minus TCO by THO minus TCI. So here there is a difference. In wordings, both these can be expressed in the same way. How can we write the log mean temperature difference for a heat exchanger irrespective of whether it is parallel flow or counterflow? That is equal to temperature difference at one end minus temperature difference at the other end. Temperature difference at one end minus temperature difference at the other end divided by log to the base C temperature difference at first end by temperature difference at second end. So parallel flow, this will be THI minus TCI, because both hot and cold will have the same end inlet and same end outlet. Whereas for counterflow, the temperature difference between hot and cold at the first end will be Thi minus Tco, and at the second end the Tho minus Tca. It is like this. So you can write LMTD is equal to temperature difference at the first end minus temperature difference at the second end divided by logarithm of temperature difference at the first end minus temperature difference at the second end. These are the relations for LMTD which we have derived. Now in a problem, suppose we need to find out log mean temperature difference of other type of heat exchangers like cross flow heat exchanger or shell and tube heat exchanger. In cross flow and shell and tube heat exchangers, we will modify the equation for counterflow by introducing a correction factor. Introducing a correction factor F. If we are using any heat exchanger other than parallel flow and counterflow, using any equation other than parallel flow and counterflow, delta T for any other thing is equal to a correction factor multiplied by delta T, assuming it is a counterflow. So first we calculate the LMTD for counterflow using counterflow equation and multiply by a correction factor. So this correction factor should be obtained from charts available in data book. So for other flow arrangements, cross flow and shell and tube heat exchangers, F is called the correction factor for the respective type of the heat exchanger, which can be found out from charts. So if we see the maximum value of the correction factor will be that for the counterflow equal to 1. So these are the charts available. These are taken from a textbook. The same charts are available for available in the data book also, HMT data book by CP Kodandaraman also. So this is a correction factor F to determine LMTD for cross flow and shell and tube heat exchangers. So there will be 4 charts available. The first one is shell and tube heat exchanger, 1 shell pass and 2, 4, 6 etc. number of multiples of tube passes. 1 shell pass and so 1 shell pass and 2, 4, 6 tube passes correction factor. So the correction factor, there are number of charts. Y-axis is for the correction factor and x-axis is for a parameter called P. P is determined by T2 minus T1 divided by T1 minus T1, whereas small t is used for the tube fluid and capital T are used for the shell fluid. So small t is for the tube fluid and capital T for the shell fluid. So parameter P is equal to T2 minus T1 divided by capital T1 minus T1. So we find this parameter and one more parameter is there. This is R. R is equal to T1 minus T2 divided by T2 minus T1. T1 minus T2 is the temperature difference of the shell fluid. T2 minus T1 is the temperature difference of the tube fluid. Temperature difference of shell fluid divided by temperature difference of the tube fluid. This is calculated in such a way that this will always be a positive quantity because T1 minus T2 and T2 minus T1 here. So which will have units like the different curves like 4, 3, 2, 1.5, 1.8 like that. And x-axis T2 minus T1 divided by T1 minus T1. From these two parameters we can obtain the value of the correction factor, and any value in between these like 0.2, 0.4, 0.6 etc. and also like 0.5, 0.55, 0.6 etc. Any value in between these values you have to suitably interpolate the values. So from this we need to find out the correction factor, and this correction factor is used in this equation if the heat exchanger given in the problem is anything other than parallel flow and counter flow. Now we can familiarize the titles. This is shell and tube. One shell pass and many tube passes. Whereas this is for two shell pass and many tube passes. One shell pass, 2, 4, 6 tube passes. Two shell pass, 4, 8, 12 tube passes, like that. And if it's a cross flow heat exchanger, we have two more. Single pass cross flow with both fluids unmixed. Now if you remember our first video lecture, this is single pass cross flow with both fluids unmixed, and this one is single flow or single pass cross flow with one fluid mixed and other fluid unmixed. The figure also gives this. So capital T1 and capital T2, small t1 and small t2. It's like this. We can use these charts and the figure, the schematic diagram given alongside to find out the parameters P and R and to get the value of correction factor for LMTD for the corresponding thing. We will have only 4 charts. Now one more thing, what will be the case if one shell pass and one tube pass? So in one shell pass and one tube pass, we can assume it as a counterflow heat exchanger and calculate LMTD based on that. That's why the chart for the same is not given here. So thus we come to an end of the second lecture and derivation of LMTD. This LMTD will be used for the analysis of heat exchangers. Bye for now. We will again meet in the third lecture, and that will be a demonstration of the LMTD method for analyzing heat exchangers.